if I counted correctly, this should be lecture number 11 already. Week number 6. And we are talking about the chapter 4 is relativistic field theory, classical relativistic field theory, and we're talking about 4.4 relativistic field equations, and we've been talking extensively about all these representations, and we found there's the simplest one is the scalar field, and so the scalar field equation is the box, or say du phi equals 0 is the massless field. Then you have, yeah, it's just the weight, the relative weight equation. If I add a mass, then equally there's some other constants, and there's a 0. Have you ever wondered why there's a C in this formula? Where's the C coming from? That's nothing so weird. Where's the C coming from? We're talking about relativity, so there's C all around, it's the speed limit. Where's the H coming from? Because we're talking about classical field theory. Well, why is there an H bar in this business? We haven't quantized yet.
Maybe there's an H in the field itself and then it cancels out.
Then you have it here, right? If there was a proportion to H bar, then we'll get it here. But the thing is, when we talk about classical physics, we don't have the waves. These are energy and momentum. And here I kind of have a wave, so I have wavelengths. And since I'm describing my particle as a field, I've chosen kind of to use a wavelength, and there's this relation between the momentum and the inverse wavelength. I get my H bars in there. If it was an electric field or so, it would be a vector, but now there wouldn't be an H bar in it. It would be just a different thing. But here I'm thinking of particle, and I'm choosing a wave picture for the particle, and so I should write this in terms of I can get rid of it if I in the exponent of the Fourier transform, I have this combination. It really is the e to the I kx, and there's no H bar, and I have the field. But since I want, I'm going back and forth between the two, then this sneaks in. But it's really just a conversion thing. That would clear what didn't clear to me. Say this. So if it is a field, and you don't have the particle picture, you write the K and there's no H bar. If you want to use P's in there, you have to give yourself an H bar, because this is just the usual conversion between the two things, which is coming from quantum mechanics, but it's just now a way of writing it. It's basically like last time you caught me talk about spin, and you say, wait a minute, this is classical physics. Where's the spin coming from? That was also like prematurely looking ahead when quantum mechanics enters, and then we have the spin. I don't have any erasers here. Only the wet one. Oh. So that's my massive particle. We haven't talked about the complex field yet, but I didn't see the need. I'll talk about something complex in a minute, so I'll say it now. We could also have the complex field, the phi. I mean, you don't even see it. You can write the same thing for a second one. So this is number one, this is number one, and you write it for a second one, two, and then you use the second to be the imaginary part of the first, and it's a linear equation, so you can superimpose it, you can put i's, and so the same equation works also if the phi is a complex field. It's just the two copies of a real scalar field. Why am I saying this? Because later I'll be counting degrees of freedom, and if I have a field and it's complex, then it has basically it comes with 2 degrees of freedom, 2 real degrees of freedom. And the second degree of freedom is also prematurely speaking, the antiparticle of the first. So complex conjugation brings you from one particle to the same particle with the opposite charges. And opposite charges you usually call the antiparticle. In order not to let this hang just in the air, one more comment. If you have your complex field phi, that's complex valued at every point in space, then you could choose to change it by a phase, e to the I, then let's call this Q, and let's call this angle, and then so changing your field by this tells you if this guy looks like our Lorentz transformation, right? With some I, then a parameter, and then a generator, sometimes written like this. So this is the parameter, this is the generator. And if it's just the number up here, then it's not our Lorentz thing or whatever complicated group it is. With just the number, it's U1. It's a number, complex number with unit modulus. So something that is on the unit circle. And that's one of these numbers. So the U1 symmetry that changes your fields by this complex phase is related to the electric charge. And this Q is the representation of your field under this U1. Like it was here, the T, whatever you put there, whatever generator you put there, it's the representation of the field. And then we classified it in different representation of the Lorentz group. And so this is the one that was the 0, 0 is writing as the left and the right as you choose. But you can have more symmetries, and very soon we'll talk about lots of symmetries, and one of them will be this U1 symmetry, and constructing it, it's the same way as here, it's even simpler, because the generator is just a number and you have this thing. And you can have fields that transform with different numbers here. You have a choice. There was a choice there. Usually they change in dimension. Sometimes the dimension is the same. The matrix dimension is the same, but they're still inequivalent representation. You had several 4-dimensional ones, but there's just a selection. Here it's a continuous family, right? Whatever number Q you put there. That's just because if you have 2 transformations, then it's as good as you have this. So e to the I to alpha is a representation because 2 composed is the same as 1, and there's your composition law. So it's a representation for any Q, and now the Q, back to physics, is the electric charge. So when you know how your field transforms under the U1, then you know what its electric charge is. Isn't that fun? And say you have a real field. What representation of U1 does the real field transform under? So this is real, and it should stay real, just because it has always been. And so there is no way you can multiply this sensibly by something, except for Q equals 0, right? You don't want to have any. It's the trivial representation. So the real field has a trivial. It transforms in the trivial representation of this electric U1. Therefore, it's neutral. So a real field is neutral. Also, like talk about, like giving you and the complex one can have any charge you want, but it's charged. And the two components of it can be then interpreted as the, once we quantize, as the particle and the antiparticle. Yes, yes?
Maybe you said the real field, and what else that we interpret as a particle?
Well, if it's justified, it will then, once we quantize, so well, let's do it now, since you asked. Complicated though. If we want to solve this equation, this is in ordered space. Usually you go to momentum space. We did this also before, so you have the phi of x integral d for p phi d. These are the support vector e to the minus ip times x over h bar, I guess. At some point, I'll set this to 1, then you won't even ask where do I stand in h bar. Now we have minus p squared from here plus m. It's getting annoying with the constants anyway. So this is times phi of p equals 0. This is just a number. If the product of this number and this number is 0, one of the two has to give. We don't want this to be 0 because then we have lost our particle or lost our field. So this should be 0. Then we find so p squared should be m. Where's the square coming? Did I do this wrong? I did this wrong. You didn't complain. I'm sorry. This is the mass term for the Weyl spinors. This should be all squared, right? It's dimensionally. This should be the squares. Because here it's squared, so this should be 2 energy units, and they just get squared because m did. So now it looks even better. And this is the p0, and the p0 is e squared over c squared, and then we have minus p vector squared, and then we have p squared equals. I'm deriving this because I don't trust myself getting all the factors, right? So we have this, and then we have e equals plus or minus c squared p squared plus m squared c to the 4. So we have both energies. We don't really like the negative energy because this is a free particle, and where should the negative energy come from? But formally, it is a solution. Now, let's define an E with an index P, which you could really think of, it's an argument. I mean, this is supposed to be an E where you stick in a P. But it's an index because everybody does it, and this gets sort of in the way. So it's hidden in the subscript. But it is defined as this thing with a positive sign. That's m squared c to the 4. And then these choices that we have is then E is equal to plus or minus EP. Just to not mess people get the signs confused, because they're going to change signs and yeah. So E with the subscript P is always the positive square root, and this E can be positive and negative. So we have positive energy and negative energy solutions formally. Then I have to say this somehow. I have a phi. Well, let's just be honest. So what you really have to do, without jumping any steps, you say this P is this phi of p is some function, what's the name? And also it doesn't have a tilde yet, which is proportional to the delta function of p squared, p squared minus m squared c squared over h bar squared, and then we need a name. We have a name. I'm tempted to write phi tilde of p vector, because now here you could think the phi is a function of four variables. Your momentum space, the p vector, and the p zero, which is the energy. And so it could have values everywhere. But if the first factor isn't zero, then this has to be zero. So it really means that your function that you have only lives on this mass shell. This is a hyperbola, right? If p is zero, then E is m. That's this value where you hit the axis at m. And then if p goes large, it becomes a straight line, because then you can forget about this, and then E is proportional to p of the value. So that is the positive energy mass shell, and then you have a negative one, and I have colors. And today I'm going to try purple. And so this is the negative, I don't know why purple, but this is the negative energy mass shell. And only there is your scalar field non-zero, right? Why? Because outside the mass shell, this is different by different non-zero, and then that would be non-zero, and it wouldn't satisfy your thing. So you have a just on this hyperboloid, a non-zero p. So then I'm saying, okay, but for every p vector, you can choose your own value. You can choose whatever you want. Like here, you can choose the value, and then the p0 is then fixed by this thing. So that's just dangerous, right? Somebody could get the arrow, and then you don't know which one you're talking about. But this is the generic one that depends on all four, and this is really the freedom you have, and the zero component is set to p0. The zero component of the momentum is set to e thing, or minus, right? If you then do the putting thing in the two parts, like this can be solved by plus or minus. Now, where am I going? Okay. I want to.
Also, really quick, I think on the first board, which should have been minus h bar squared, and there's also the square still missing on the
The first board here?
Yeah, the lowest equation.
Oh, yes, that's the same.
And also the p is missing an h bar squared, no?
Where?
The minus p squared should not be minus p.
Over h bar. Oh, yes. Oh, yeah. I don't know what's wrong. This is not a good day, I'm telling you. Because this doesn't make dimensionally any sense. So then we have this, it's cancelled here. And that's p squared. This is the mass shell. Yes. Thank you for helping out. Like really, everybody just writes this, and I'm getting confused. Now, I don't know what to call it. So I'm going to file X, and I want to transfer transform back. And then you have to use this thing. And then I'm using this delta function. And then I end up with some function e2 of the momentum. And I don't know how to call this. Minus, and so this is my positive energy solution. So the zero component is this thing. Now, here it is. H bar is equal to C is equal to 1. Because otherwise I would have to put an H bar here again. And then I will forget, and then I'll get into trouble. So I P vector times X vector. And here we need a name. And what do people do? I guess A, P. This is just the amplitude. It's essentially this thing, but only for the positive part. And then we have another one, and let's call this B. And this is then where the E, so then we had a minus E here, but I integrated over the energy part using this delta function, and then this turned into minus P. And then nothing changed here. I still have that. And now, what was your question?
Like from the field, how do we even get to the antiparticle term?
Right. These things will be your oscillators. If I quantize, and this is my quantum field in, then something has to be operated on this side. So this will be an operator and an operator valued field. And these will be the operators, and they will obey, hopefully, they will the ladder algebra. So we know how many oscillator ones. So they will create and annihilate some particles in our focus space, like we did in lecture 4, I guess. And now we don't see this, but I'm just claiming one will produce. Now here's the thing. We need to figure this out. We will try to derive this. If this is a real field, then these guys have to be complex conjugate of each other. Almost. So first of all, if this was the complex conjugate of this, then they have to be the same. I mean, a real field means that the complex conjugate is the field itself, right? And so there's a relation between these two. But it's not that this is the combination of this because of this same sign here. But then people say, okay, I do a change of variables. I substitute P by minus P. Then I get minus P here. It changes the sign. And I love to, no, I'm not. Phi of X is integral D through P. A e to the minus that's I da, da, da. And in the second I change P to minus P. Then I P to the plus I P minus I P back to X. And now this is the complex conjugate of this. And if this is a real field, this means that the B minus P star is a P. So they are related, yes?
Do we get a minus then in the formula or?
Where is the minus in the formula?
No, it's just like if we like change the
This
variables to, yeah.
No, why? Because it's I do it 3 times. I mean, it doesn't matter if I do it 3 times. I can do it once. So like the P1, and then I say Q1 is minus P1. Then this integral P1 becomes integral minus the Q1. Is that the minus sign you're worried about, right? But then I have minus infinity plus infinity here, and with the sign this becomes plus infinity and this minus infinity, and you turn them around. Yeah, I wasn't explicit here. So but this I mean, short questions, it was supposed to be a short answer. So if it's a real field, then these are related, and you only have one type of thing that you create and annihilate to the oscillators. If this is a complex field, you don't have this relation, and then you have one term that creates a particle, and the other one that creates an antiparticle, more or less. It really is. You have to look at the other thing, and they are independent. This is independent. One of them creates a particle. One of them creates an antiparticle. I could have probably answered this quicker, but we'll argue like this also for the primitives now. Summarize, yes, first you.
Why can we go with a 4-dimensional Fourier x to p, but from p to x we do a 3-dimensional?
Yes, I've been bad. Because the short answer is I use the delta function. So delta, I didn't know I knew that. Delta p squared minus m squared c squared. If delta p 0, let's call it e now. I don't have to bother with the c, so it's e squared minus p vector squared minus m squared c. Oh, c, where's the c thing? C, this. And now I have an integral d4p, which is an integral d3p and de. And I can use this delta function to do a one-off disintegration. I'm choosing the energy integral. To do this, to use the delta function for doing the energy integral. Now this is a square. I'm supposed to set everything in the integrand, every e in the integrand to the solution of this equation, but this is a square. So I first write this as whatever it is. E, you have to set this thing to 0, find the solutions, and then it's minus whatever the solution is. 0 means the root. We have done this. The solution to this equation, equals 0 is that. So these are the, so I have the positive energies, and then I have the negative energy. And then the formula says you have to also differentiate. You remember this delta formula business? Delta f of x is delta x minus x0 divided by f prime of x0. When x0 is, did you do that? No. Oh, then this is something we will learn next tutorial, I guess. Oh, now I'm not going to get to my fermions. Let's do this separately, a little more carefully. The whole steps. I want to just make a comment, and now I'm off track totally. And I didn't want to go so much off, so I skipped a step and confused you by doing that. Now I'm trying to fill this, but also not going to try at the same time not going to even further off track. So I'm going to skip other things, and then you're going to be totally confused. But the point is, I have this this delta function puts me onto both shells, and being on both is you can write as either there or there, and so you end up either there or there, and then I'm going to use this to perform the integration, and I'm left with the 3-dimensional one, and that's here. And the E that was in this thing, in the original Fourier transform here, the P has the E and the P vector. And that E with opposite index has now turned into an EB using this. So, right. Okay, what are you supposed to take away? That's my scalar field. If it's real, it is 1 degree of freedom, and it's 1 particle. And if you quantize, then you can grade and annihilate it, and that's it. This is this 1 particle that is electrically neutral in all other terms. Yeah. If it's complex, then you have really imaginary parts, so you think there are 2 degrees of freedom. And the 2 degrees of freedom are in fact a particle and its particle friend, the antiparticle. Because if you complex conjugate, so if phi transforms in this representation under U1, the friend transforms under e to the iq alpha phi complex conjugate, but this is e to the minus iq alpha, da da da. So the complex conjugate has the opposite charge. So therefore, it has the opposite charge, and you call this the antiparticle. Good. Yeah. Huh. Now let's go to the next step, the Weyl. I'm at the moment, I'm really only repeating. The Weyl spinor, and with 1/2 0, it's a sigma bar mu e mu psi left because of this is 0. And we saw, well, first, this is it's a Masterkurs thing. But it's complex, everything is complex here. Your sigma matrices have i's in them. So you can complex conjugate them. The complex conjugated one satisfies an equation too, but the complex conjugate satisfies this. You sigma to psi left star equals 0. So the sigma 2 is just, I don't know where to put it. Minus sign. It's just for decoration. So you can multiply with the sigma, but it's the complex conjugated one. It's not 0, it's not a real field, it's a different one. So this is the particle and this is the antiparticle. And we saw that the particle, the left-handed one, has helicity minus 1/2. And here, this is the opposite equation. It's basically the right-handed one, the right chiral one. This is the wave equation, or the field equation for a right-handed particle, and this is helicity plus 1/2. So my Weyl spinor, one left-handed one, describes a left-handed particle, and along with it, a right-handed antiparticle, because it's complex, and you can complex conjugate it, so it's another thing in there, and it's a line. There's 2 degrees of freedom in it, and these are the ones. Now, the other one is just the opposite. So if you have 0, then you have a right-handed particle together with its left-handed antiparticle. So analogous. Then we added a mass term. Then we add which is called a Mariana mass term one, because we're adding mathematical expression to the term. Then sigma bar mu psi L, and what do we write? You have to have something that transforms in the same representation as this does. So it's exactly the one. If you only have a psi L around, you have to turn it into a psi something that transforms in the right chiral representation. So it's this. And then we have to figure out what goes here, and this is the mass. Really MC over H bar without the square. See here, this is what was my confusion. But here it's only one. This is one derivative, one n. And now this is an interesting thing. It couples particle and antiparticle, the psi and the psi star. So you don't have them independently anymore. You can also not do a U1 transformation. You cannot do e to the IQ alpha on this. You can change this by a phase and have the same equation, because if you change this by a phase, this rotates one way and this the other way. This is the antiparticle to this. So you don't have, well, this is 0. It doesn't have any charge. So the particle is its own antiparticle, like a photon, if you already know where. And so you're losing sort of the antiparticle is reduced into just one, but it has both helicities. Because this first bit, like this, is really the PL, or that's the PR. It's PR on psi L is zero, so it's telling you there's no right-handed bit, it's just the left-handed part. But here, this is not zero, it's that. So therefore, it has an undefined helicity, so it has really both. This is particle equals the antiparticle with both helicities, rather than just one or the other. So it still has 2 degrees of freedom, but it's kind of losing its antiparticle. Let's call him he. The left-handed particle had a friend, its antiparticle, but now it gets rearranged. It loses its charge, there is no antiparticle anymore, but therefore it gains the other helicity. And that makes sense because if it's massive, it doesn't go at the speed of light. So if it moves somewhere, like this way, with its spin this way, so this is a p and this is the spin. And now I am really fast. This is your reference system. So with respect to the blackboard, it goes this way. But I'm faster, so I run past the thing. But in my reference frame, the particle goes backwards. Right? I'm faster, so it's going backwards. I'm passing it. It still spins the same direction, but then the scalar product changes the sign between this and this. So the helicity changes sign because the projection of the spin onto the reverse momentum is the negative of this. So by passing it, I have changed into reference frame where the helicity has changed the sign. And that's okay because my particle can have both. It's a massive one, so it's not the speed of light, and both helicities. For different observers, every observer gets their own observable there. You can have plus or minus one. If this goes, it's speed of light, you can't pass it, so the helicity is the same for everybody. Now, that's that story. And today, we're talking about the Dirac. If there's any time left. I want to do something like this. I want to start with my Weyl spinor. And I want to give it a mass, but I'm not going to use the same object with the complex conjugate because I want to keep my antiparticle, right? We have massive electrically charged particles in this world. So we have to come up with what we do with this. This isn't massive, this isn't charged. And this does now both. And I'll simply write a different person. This is now she. It's a different object we didn't have. I have to have 2 Weyl spinors. So this is a different Weyl spinor, but it's right-handed, so it also has its own equation of motion. So that we will start with this. And this I want to have massive, so I'm going to write it CL here. They work together. For this Weyl spinor to be massive, it has to have some mass term. So suppose there's an M, but let's just see if all the constants and the i's work out. Let's call it K for now for a constant, and then this is something that transforms right. Right in both meanings. So it's the right representation. When I'm writing this. So this is my field content. I'm not thinking of a system of 2 fields, not just one scalar field, one it's on 2 Weyl spinors. One in this and one in this representation. I can write this equation down. And here I don't know what it is, so I have to I'm fixing this because everybody should be massive. Now, let's apply this operator, matrix, differential operator, to the first equation, then this will hit the R and I can use this sign. So here, multiply by sigma nu d nu, and then we get sigma nu d nu sigma bar d u psi L plus k sigma nu d nu psi R equals 0. This we did before is just the box. It's d nu d nu. When we discussed the Weyl spinor. And this guy is minus k tilde psi L. So the equation now is d mu d mu psi L minus k tilde psi L. And this is supposed to be this thing, so you know what the k is. So k tilde should be minus n squared, t squared, or h r squared, or just n squared. And now it's your choice. If you did the same thing for the other way around, if you did this, we would find the very same thing. Always the tilde was there. And same condition. And now, whatever we want to do, I think the fairest would be to make the two k's equal, but we're not forced to. But that's one way of solving this condition. So just to say k is k tilde, and then I have to give everybody the I, and then I have an m b over h bar. That's one choice. But clearly not the only. I could also make this one the negative of that, and then I don't have the I. One gets the full minus sign. Now both have an I, half a minus sign. And then the equation that we proposed, both of them look like this. U psi L plus minus I. What? I don't like I. I plus I, right? Let me just see if I did want that minus sign. Do I want it? Do you know? Oh, you don't have it yet. Damn it. I want it. Okay. And sigma mu d mu psi r plus I MC over h bar psi r equals 0. So this is now that we had. It's a particle, massive, and charged. It has both helicities. But it looks too complicated. Now we have two equations. One more comment about the sign. Since you can redefine them independently, I can absorb any sign. I can just, if you wanted a minus sign, you can get your minus sign by just defining your I, this is yours. Right? It's a negative one. Then you get a minus sign with yours, and here as well, and then you multiply by minus one. So this is really arbitrary. That's why you have to look up what conventions you want to choose. And I'm choosing Peskin Schroeder or whoever is available. So that's this sign. But now, as I said, I don't like two equations of motion. So let's put them together. And there will be a matrix equation.
In the right equation, shouldn't there also be a psi L and not two psi?
And there should be a psi L. Right, they're talking to each other. And now we are making a matrix equation out of this. So it's psi, it's my psi L, psi R. So this is two components. This is another two components. So guess what? The whole thing is four components. Just to be really honest, we have now this thing, four components. The Dirac, this is a Dirac spinor. And it has four instead of two, like the Weyl spin. In fact, it contains two Weyl spinners, a left-handed and a right-handed one. The bottom is this. So the whole thing doesn't look like it has a chirality because it. What's the equation now for this psi? So we want to multiply this thing with by matrix, and then the two lines should be this. And now we also have a choice. First of all, I don't want the I over there. And people don't want the I over there. So let's multiply the whole thing by I, minus by I guess by I. Then you have I sigma bar mu du psi L minus M. Get rid of the M and this is now C over H bar psi I equals 0. And here I sigma mu d u psi R minus MC H bar psi L equals 0. And I want on the diagonal, I want the masses. So the second equation is minus MC H bar. I'm writing the second equation first because if this comes here, then the mass term is the, sorry, I was writing this first, and the other one is to be this. I sigma bar, not bar, mu d mu, yeah. And then here it's I sigma bar minus MC H bar, right? Perfect. Now we have put everything into one equation, a matrix equation. Now, yes?
Couldn't we get rid of the I altogether if we just redefined our psi R to be, let's say,
Yes.
I times the
Yes, we could. Then basically the K is plus M and the K tilde is minus M, and then the product is still this thing, and then you don't have any I's. But I want to follow the mass, what everybody, most of them do. It kind of has a reason, reality and emergicity, and sometimes you want I's. But on the other hand, it seems like every possible option that you have, somebody has taken it and written a book about it. So now, okay, I said I wanted one equation, but I don't really want a matrix. I don't want to see a matrix. It's too big. So now we're turning this into something smaller. This object is really minus M C H bar 1 1. I guess. And then this other bit plus there's an I, and then there's sigma mu, sigma bar mu here, and it's all multiplied by the mu. Right? I'm taking out everything except this is a 2 by 2 matrix and 2 by 2 matrix, and this is a 2 by 2 matrix as well because it had to. It's acting on this everything, but it is really like here there's a 1, which you don't see. This is this one. Does that make any sense? And now these are 4 by 4 matrices written in block 2 by 2. So this is a 2 by 2 1. This is a 2 by 2 1. So it really is a MC over H bar big 1. 4 by 4. And then here, I'm going to just call this gamma mu d mu. Where gamma mu is nothing but the definite is defined by this. So define. Because I want to be able to write it more compact. And then this equation here reads I gamma mu d mu psi minus MC x bar psi equals 0. Now it's one equation rather than two, but then it is a matrix equation. These were matrix equations already, 2 by 2 matrix equations, because it was Pauli matrix. This is a 2 spinor. Then it turned into a 4 by 4 matrix equation, and then we hide everything in the gamma matrices. And so it looks very neat again. This is the Dirac equation. I am, well, this is the, so the headline goes home, I guess. This is the field equation. And these are called Dirac matrices. And on some problem sets, I've already introduced you to them, just work with them a little bit. And here you see how they appear. And they have nice properties. If you want to do any computation, and don't want to spell it all out, right? You can always spell out everything in 4 by 4 matrix form. Then you don't see the matrices, you don't ever need them. But nobody wants 4 by 4 matrices. I hardly want 2 by 2. So what if you want computations, what do you need properties of the gamma matrices so that it's kind of you work through this. And the first one that you see is that the trace is 0 because there's 4 zeros along the diagonal, so the trace is 0. Fine, that was easy and not really important right now. But we did it because it was easy. Then if you multiply 2 of them, you get 0 sigma mu sigma bar mu 0 0 sigma mu sigma bar mu, and then sigma mu sigma bar mu, nothing again, and then sigma bar mu sigma mu. And that looks like something familiar. If we had the same in the opposite order added to it, then it would be this metric, eta mu nu. So let's do that. Let's compute the sum gamma mu plus gamma mu with the opposite one, and then you get this thing in the opposite order in here, and they are 2 eta mu nu's there and there, and so the whole thing is a 2 eta mu nu times the 4 by 4 unit matrix. And that's an important one. And we also saw this, at some point I claimed it. By the way, this people write as the anti-commutator, gamma mu. With the plus, it's just a definition. And this is called the Dirac algebra. Mathematicians have formalized this whole business and made it more abstract and unrecognized, so it's like more general. And this is a kind of Clifford algebra. So sometimes you see Clifford algebra instead of this, but in the special Clifford algebra it looks like this. But it doesn't even matter. It's this. What does it mean for you? For us, it means the following: if you have both indices the same, let's say you have 0, mu and mu is 0. Then you have it's squared here, right? You have 0 and gamma 0 times gamma 0, and there's well, so there's two of them. And on the right hand side, I have 2 with eta 0 0. Eta 0 0 has in our convention a plus sign, so then we have 2 identity matrices, canceling 2 so identity matrices. This gamma 0 squares to 1. If you have any other, then the metric here is negative, so they square minus 1. So this is really what your Clifford algebra this is one thing your Clifford algebra tells you. 0 squares to 1, spatial square to -1. And if they're not the same, they're the opposite, then you have mu opposite means, I don't say opposite, it is opposite, I meant different, not the same. Like here the same, here opposite doesn't exist, they're just entire. If mu and mu are not the same, then this is 0. And then the plus equals 0, so we can bring it to the other side. So they anti-commute. If we exchange 2, the order of 2, you get a minus sign. I mean, this equation is nice, and you can use it sometimes, but what it really means is square root of 1, square root of -1, and they commute. Now, this whole Lorentz business, what's the time? Now we want to this transforms under Lorentz transformation. It is both. Like mathematically, it is a direct sum of 2 representations. Just because we put them together, side L, side R, we have extended our vector space. So the first representation used a 2-dimensional vector space, and you just put them together like this, and that's a direct sum. So you can have vectors in this and the other direction, and that's what that is. So the representation is formally called this. But at the working level, it just means it transforms psi, the Dirac spinor transforms by this UL UR. This is now a reducible representation because it's in the block form, and it's reducible into these 2 parts. So this big matrix is the representation. And now this is e to the I have alpha k sigma k plus 1/2 beta k sigma k from e to the I have alpha k sigma k minus 1/2 beta k sigma k, and then here. So I warned last time, I'm going to warn again, that this k had to move up. Like earlier, we had only Pauli matrices and just a spatial index 1 to 3, and you just label them 1 to 3. But now, since we package them into a sigma mu with upper and lower indices, this is this, and the lower one is this. It's now not clear if I write sigma k, if I write sigma 2 for example. What is this? Is this the second Pauli matrix? Is this 0 minus I 0? That would make sense. This is what it always been up to now. But now you could also think it's not the second Pauli matrix. It is this the second component of this 4 vector. But then you look up what it is, and that is the negative Pauli matrix. Then this is I minus I dot, and then you get upset. And next time I'll introduce this thing, I'll probably use a different name for it, like tau. Sometimes people use it called tau, and then you don't have this confusion, but it's too late because it's in there. And therefore, not to have this confusion, the Pauli matrices get their indices now up. Then it's up and then no sign. So this is all just to show that there could be a conflict, or let's erase the conflict, and the Pauli matrix have the indices up. It's more natural anyways, but it's the X as well. It's like we have always been talking about vectors in 3-dimensional Euclidean space. You have the index down and everything was good until Minkowski came and put it there. And then once you put it up there, the k that's now downstairs is the negative of what you always had downstairs. screen 3. Now. I don't like this block form. Like here, I want to express this in terms of my gamma matrices. I want to write this as one big object. And to figure this out, I have to expand it first, like there. And also I'm going to expand it in the parameters, the small parameters. So this is first the unit matrix. Do it up here first. Let's first expand. Plus I have alpha k sigma k plus half beta k sigma k 0, 0, 1 plus half alpha k sigma k minus 1 half beta k sigma k. So here is also plus higher orders. Now this is 1. Then I have I say the one I or I have I have alpha k, and in here it's sigma k, then plus 1 half beta k, and here it's the opposite, sigma k minus sigma k. And I want the whole thing to look nice. What does nice mean? If I have my 4 vector, the representation for the 4 vectors, x mu transforms, there's one way of writing it, it was this thing, e to the I omega alpha beta m alpha beta, and then mu x mu. This is the last problem set, and that's nice because you don't even see difference between boosts and rotations all in one, and that's what I call nice. But then the relation was omega 0 k is the boost, so it was antisymmetric, and the ij is epsilon ij k alpha k. That's the, so it's rotation and boost in there. And this is what I want here. I want this to look like e to the pi omega, obviously half. The half is there because you basically double count with the antisymmetry. That's why you have a half here. Not that it is a spinor representation, it's just because of the two entities. So I have omega alpha beta, and then whatever is necessary to make this work with psi. So this is what I want. And I'm trying to identify now what the exponents are. I know how my omegas are written in terms of angles and boosts. And then whatever comes, right? So this is expanded 1 plus. Did I need to write the psi? I mean, either I'm looking at the, you know. I need another parentheses, right? I want to be fully honest. It's applied to it. I could have just looked at the matrix. I didn't, my bad. Now I have, and just this thing, but I'm going to split this up. Let's look at one index 0. The other can't be 0 because that is symmetric. So there's just a k, and then s 0 k here. And then the other goes to 0. So it's omega k0 s k0. This is going to turn out to be the same, 2 cancels. Then we have this mixed one. I have omega ij s ij. The whole thing psi. Dot. You suffering too? Yes, yes, me too. Now, we have one. This is eta. I can turn them around at the price of a minus sign and then at the price of a minus sign. They both anti-symmetric, otherwise I thought it wouldn't make any sense. And so this is the same as here, and this is eta. So I have I plus I eta k and multiplying s 0k. And this other thing is plus I have epsilon ij k alpha k s I j plus stuff and psi. Are we ready to compare now? Yes, we are. Are you? What multiplies eta k needs to be the same. So here eta k has an I. Let's do it slowly. So what multiplies eta k is I s0k, and what multiplies eta k is half in this thing. So it's a half sigma k minus sigma k 0. And therefore, S0k is minus I half sigma k 0 minus sigma k. And what multiplies alpha k is also to be the same. So I half epsilon ijk Sij needs to be I half, how convenient, sigma k. Oopsie, did it go down? Sigma k. And then cancel. Cancel. But now I also want to get rid of this epsilon. I don't want to have a. I guess you know how this works, right? And multiply this by epsilon m n k and sum over k. So I have epsilon m n k, epsilon I j k, s I j, and the right hand side is epsilon m n k, sigma k, sigma k. And this thing is a bunch of delta functions, delta mi, delta mj, minus delta mj, delta mi. So it sets the I to m and the j to n, or the I to n and the j to m. That's an oopsie. Oh dear. What is? And now this is anti-symmetry, I have the same as I turn this over, add them, divide for s, and n is 1/2 epsilon in mn k sigma k sigma k. So now this thing up there is the boost generator, and this down here is the rotation generator. So this is basically my spin matrix for the Dirac representation. This reducible 1/2 representation. And now we have these guys. But the funny thing is, they can be written in terms of the gamma matrices in a very neat way. Both of them did no. we have, and this is now just a claim, but this S alpha beta, the whole thing is I quarter, and then not the anti-commutator, but the commutator of the two. So that looks very nice, and it's very convenient if you want to do computations with this further on, like homework. And I had planned to do this, to show you that if you set this to 0 and k, for example, that you get what I have there. But now time-wise, I'm not sure. Let's start with one at least.
And this is a wrong in the equation.
Something's wrong.
And the last equation.
Yeah. Yeah. Thank you. That didn't make any sense. Now let's say, check. S0k. Now, using this formula and see if it's that, then we have I quarter gamma 0 gamma k. And now, let's see if we remember what the matrices were. They were these off diagonal ones with a bar down here. And that's of course the same off diagonal one. Now it's k with the bar k, 0. And now I quarter. The zeros component of the sigma matrix is just an identity in here. And that's the sigma matrix, and this is the negative sigma matrix. Now, if you do commutator, so the first term is, I guess, minus sigma k, nothing, sigma k, minus sigma, the commutator. Now this goes to the back, so it's sigma k, nothing, and coming from the right, minus sigma k. And I guess they add up. So we have minus I half sigma k minus sigma k. I'm not going, I don't dare to look. Yes, it's the one. It's even with the sign, spot on. Okay, so there it is. And if you did the same now for Ij or Mn really, Mn, you would be blah blah multiplying. Here would be a spatial one. So you ended up with something like not just the one, you don't see the one anymore. So here will be two Pauli matrices. And the two Pauli matrices will have an, you know, n is epsilon mn k sigma k with an I plus the delta. Since we have the commutator, there will be a second term, it will kill this, and you end up with an epsilon with the sigmas and an I. The I is going to soak up this I. The epsilon will survive, and in your matrix you'll have the case. So after some computation, you will end up hopefully no I, then 1/2 because of this. If I can get it into well, I guess it's this. Sigma k, sigma k. Oh yes, spot on again. It's a boring computation, and we have more physics to talk. The upshot is going on this board. The Dirac spinor transforms Lorentz transformation is psi goes to, we need names, we're going to get this name, lambda d psi. And the lambda d is the e to the I half omega alpha beta s alpha beta. With the s alpha beta being this. That deserves purple. Disappeared. Get some kind of yellow. This is the here, not much. You love it, yes? That's come on. Are you kidding? They are the same type. They are the same. They are the same type. It's not that this is a different one. It's I'm also always reluctant because in the Dirac algebra it's mu and nu because it's not going away. But since this thing here, not there anymore. Here, this m, the m is contracted, and it also has indices. And I find, and I don't know, I found it confusing for you, I guess. Because these indices are the ones that talk to the index on the 4 vector. So I wanted them to look like the 4 vector indices, and that's nu and all that things. And they aren't really 4 vector indices. They were just counting the matrices. We needed 6 matrices, and you could label them however you wanted. Like in the beginning, we called them J, K, K, K. Right? These are the generators. There's also 6 of them because 1, 2, 3, 1, 2, 3. Or the SLSR. There's also so however way you want to label them. But this is a convenient way of labeling with the double index, antisymmetric in the double index, because antisymmetric in the double index means you only have 6 independent ones, and you can write what they are, what these matrices are, in the super amazing formula. Like if you wanted to know what is 1, 2, the matrix with the label 1, 2, oh, you just look it up here. It's eta 1 mu delta beta mu and the other one. So this was a nice way of writing, but they are still the same indices. Also here you see it's the same because they talk to the same eta. And therefore I could have written mu rho sigma or something. But I want to be far away so that it's not confusing. But now it's getting back. They're not different. All I'm going to say is they're not different anything. What is this? It's the representation 1/2, 0, 0, 1/2, and it's not unitary. What does that mean? Lambda, if it was unitary, then this would be the inverse. That is unitary. And if that was the case, you could easily form invariants. You would just take your Lorentz, your Dirac spinor and decorate and multiply the thing, and then this is a invariant. But this is not true, and so this is not invariant. We have to figure out what is invariant. And why is this not unitary? And again, the boosts are the problem. If for this to be unitary, the exponent has to be Hermitian, right? Has to be like this has to be Hermitian with the I anti-Hermitian because you want to dagger this and get a minus sign. If you dagger this, then the I gives you the minus sign, and this shouldn't spoil the minus sign. So if this is Hermitian, everything is fine. If this isn't, then it's not fine. So this is Hermitian for the no, for the other ones, for the IJ, it's to the IJs, that's gamma I, gamma J, dagger. Oh, but we better know what. I guess we need to know what another property of the gamma matrix is. So anyway, this is minus I quarter, and then the factors in the product reverse under adjoint, so it's this, and now nobody knows what the dagger of a gamma matrix is. So gamma mu was 0, sigma mu, sigma bar mu is 0. Is this Hermitian or not? So this dagger takes this thing down. The whole thing has to be reversed. So it's this, but then also dagger. And sigma bar mu dagger. But they are just Pauli matrices or identities, so they are Hermitian. But this is just sigma mu, sigma bar mu. And now the question is this the same as the one as this? Well, this bar has shifted to the top. And it's not that it's only the same for the time part. So gamma 0 dagger, it's just identity, so that is Hermitian. But if it's the spatial one, then you get the minus sign because the spatial bar is the minus of the spatial unbar. Then it's that's the problem. Now we have the problem. And here we get a minus sign and a minus sign from this. So it's minus I quarter gamma J gamma I, but that's not the Sij because it's the reverse order, so this is minus Si. Oopsie, wait a minute, it's plus. It's plus. So this reversed eats up the minus sign that we got from combination. Yes, so these are the rotations. Perfect. Hermitian. Rotation generators Hermitian. Therefore, the Lorentz transformation, the rotation part is unitary. The boosts, I knew it from the start. Boosts are always weird, like time contraction, time dilation. It's just weird. Now we have I. So it's the same story, except for one of them has a 0 rather than a plus. But if it's a 0, then we don't use this law, we use this law. So there's one minus sign missing, and then the whole thing goes through with an extra minus sign. So this is S0K, and so this is anti-Hermitian, and therefore it's not unitary. So this just shows the point. And that's not invariant. And your homework. Into your homework, yes, your homework is to show something. So in your homework, you just use the result is to show that the dagger with a gamma 0 transforms as the inverse. So by definition, it is lambda d psi all dagger gamma 0. This is my Lorentz transformation. I just apply it to the psi here, this thing. And this is what you have to show. This is psi dagger gamma 0 lambda d to the minus 1 for all of the rotations and boosts. So what is not true is this thing. Psi dagger goes to, by definition, this, and if this was unique, this is the same as psi dagger d to the minus 1 dagger. If it was unitary, then you'd have your inverse here, but it isn't, so you don't have it. We need some object, conjugated object, which transforms with the inverse from the right to create invariants, invariant objects. And that doesn't do the job. It has the dagger and not the inverse. But if you stick a gamma 0 in there, magically, this with the Dirac matrix, see Humboldt, you'll find that this combination then transforms like this. And then as a consequence, it follows that psi dagger gamma 0, psi is invariant under all the Lorentz transformations. And since that's the case, define psi dagger gamma 0 as something shorter, like psi bar, call this the Dirac conjugate. Like Hermitian conjugate times gamma 0 is the rough conjugate, and then you can write this thing as psi bar psi. So the psi bar psi is the invariant one. And then also homework is this beautiful identity. If you have the D, with minus 1 on the gamma from the left and the right. Yeah, the minus, yeah, you have to have that, right? This is the same as the corresponding Lorentz, the representation of the Lorentz transformation on the four vectors. It's totally weird. These are the e to the I half omega alpha beta s alpha beta, and this is the e to the I half omega alpha beta m alpha beta, and they talk together, and it's a beautiful thing. And you'll show this as well, and that can be used to not only create variants but four vectors out of Dirac spinors. And I think this will be the but can you go over I guess. And you can use this thing to create. So this identity says if you take your bar one and before closing it with another psi, so psi bar psi is invariant, as we said, because psi bar this is psi bar transforms psi bar with this inverse, and that by the lambda t, so that if you stick in a few gamma matrices, mu, rho, so many you want, then it transforms to psi bar lambda d to the minus 1 gamma mu, gamma rho, lambda p psi. But now you can stick in here lambda d to the minus 1, to make it more complicated, and here as well, lambda to the minus 1. But since you have this identity, the first gamma matrix with its neighbors is a Lorentz transformation. And the second, so they get all Lorentz transformed. The answer then, after the transformation of this thing, is equal to lambda mu, lambda rho. These are the indices we have here, and then we have a psi bar, gamma, and so on, psi, and they need to be contracted. So let's call this. We could call this alpha beta. What do you want? Do you want alpha beta? Alpha beta gamma, and so on. So beautiful. These are the factors that you can create out of the Dirac spinor and a bunch of these gamma matrices. It's very similar to what we did for the Weyl guys. I guess this is an almost good way to stop one very last notational thing, because now this index up here, which was just a label at first, transforms under those Lorentz transformations. It looks really like a four vector. This set, gamma mu, is this set is a four vector of 4x4 matrices, and it transforms like you would think any four vector does, and therefore we can also define the covariant one by eta, lowering this thing, so it just they allow us to pull this down, and we can then write if it's some vector times the gamma matrix. It's just the scalar product of some vector with the gamma matrix. And Feynman thought this is too much writing. Let's write it as the slash. It's not cancelled. It is just what it is here. It's the scalar product of the four vector with the gamma matrix, and then it's called the Feynman slash notation. And here is the last one of the day. Now, the Dirac equation is this. And it's even shorter if I leave out C's and H bars. There it is. This is the contraction of the four vector B with the gamma matrix, and therefore we could use it. Yeah, with this little equation, and I hope I get this right. Punchline. Somebody asked him, I guess, what does this equation describe or so? I'm not retelling the story really right, but the answer is kind of, well, it explains everything in chemistry, everything in biology, and most of physics. But really, this is electrons, and what he was hinting at, like electrons, all this chemistry is moving electrons around the nuclei, and so this is really a huge equation, but it's not all of physics because you still have other particles that you want photons in this course. I don't know, it wasn't particularly funny, but anyway, thank you.